Hi, today we're going to talk about linear regression. So the goal of this section is, given more than two data points, it's rare that the data points will lie on a single straight line. So here we want to learn how to find the line that comes closest to passing through all of the points from your data set. So let's start with a few notes. I'll zoom in here. The GDP means gross domestic product. The gross domestic product is a measure of the total market value of all goods and services that are produced within a country. Definition: the observed value is the actual GDP, so it's what's given to you. The predicted value is the gross domestic product predicted by a linear equation. The residual is the difference between the predicted value and the observed value. So in other words, this blank is residual. The residual is equal to the observed value minus your predicted value. Okay? Graphically, the residuals measure the vertical distances between the observed data points and the line. The residuals tell us how far the linear model is from predicting the actual gross domestic product. So throughout this section, I'm going to refer to this table here. And this table shows the past and projected per capita gross domestic product of Mexico for the years 2000 to 2014. So for the year 2000, the per capita was $9,000. Okay, and so on. Okay, so taking a minute to plot these points on this TY coordinate plane, you will have 0, 9. So just remember that when you're reading a table, whenever you look at this point, it corresponds to the ordered pair 0, 9. Okay, so when you plot that point, you will have 0, 9. Plotting these data suggests a roughly linear growth of the gross domestic product. So specifically, what happens, it looks like, as we look here, it's a rough linear relationship between T and Y, although these points clearly do not lie on a single straight line. So now what we could do, we could sketch some lines here to see what would be a good fit for this data. Now, if we take a look at this green line, that does not accurately represent these data points here. So the green line, that would be a terrible fit here. The green line is a terrible fit. And if we look at the red line, that's worse. So the red line would be a worse fit. But if we look at the blue line here, that seems to fit these data points better. So we would call that a good fit. Now, examining our terminology, or pointing out what our terminology means in terms of the data points and the good fit, here, notice that the black points represent our data points, as we've already pointed out. So those are your observed values. I'll mark them in yellow. So just putting them underneath, these would be your observed values. Those are your observed values. And then the blue line we would think of that as our predicted, since it's a good fit. So that's our predicted value. And the vertical distance, let's go here. Let's go here. The vertical distance between our actual observed value and the line, that's your residual. So if we zoom in here, this vertical distance, that vertical distance here, this is our residual. Okay, that's our residual. So we see that our residual is our observed value minus our predicted value. Now, if we were conducting research for a company that wanted to actually expand in Mexico, we would be interested in the current and projected growth in that country's economy. So this is actually useful information. Linear regressions are applied in business. Now, suppose we have data points x1, y1, x2, y2 out to xn, yn. So suppose you have a few ordered pairs. If the variables bother you, remember that you can think of these are just numbers, okay? The n quantities, y1, y2 out to yn, are called the observed y values. These are called the observed y values. And if we model these data with a linear equation, y hat equals mx plus b, then the y values we get by substituting the given x values into the equation are called the predicted y values. So these would be the predicted y values. So y1 hat would be mx1 plus b. y2 hat would be equal to m times x2 plus b out to, and this should be yn here. So we're going to write y sub n equals m times x sub n plus b. So make sure you make that correction there. Now, a few things to note. This y hat here, this y hat stands for the estimated y or your predicted y. Again, it's your estimated y or your predicted y. Okay? And to find the corresponding predicted y values, then notice that what you're doing is you're substituting whatever x sub I corresponds to this one. For example, you'll be substituting x1 for x here. Here you'll be substituting x2 for x, and so on. Okay? Now, another definition, and then we'll go through an example. If we model a collection of data x1, y1, x2, y2 out to xn, yn with a linear equation, y hat equals mx plus b, then the residuals are the n quantities, which is your observed value minus your predicted value. So that would be equal to y1 minus y1 hat, y2 minus y2 hat out to yn minus yn hat. Okay, the sum of squares error, the sum of squares error, abbreviated is SSE. This is the sum of the squares of the residuals. So your SSE is equal to this residual square plus this residual squared plus everything out to this residual square, the nth residual. Okay? Now let's go through an example. Let's figure out what we've been talking about in terms of an actual example. So we're going to refer back to the table 1 from page 2 on the gross domestic product in Mexico. And we're going to compute the sum of squares error for the linear models. Y equals 0.5t plus 8 and y equals 0.25t plus 9. So these two lines. Which model is the better fit for the data from table 1, page 2? Okay, so we want to start out by creating a table that shows the values of t, which were in you typically think the xy coordinate, so you would have, but instead of x, we're writing t and comma y. So your first one was 0, 9. So here we have that the values of t, then our observed given values of which are our y values, and then we're going to have the values predicted by the first model using the line y hat equals 0.5t plus 8 because y hat represents our predicted. Okay, so we fill in our t's. This is what we have. You fill in your observed values. This is your y. Now your predicted value, what you're going to do is take your t. So you're going to be zooming in on this value here, and you will get this predicted will be 0.5 times 0 plus 8, and that's equal to 8. So our first predicted y value is 8. Now pause the video and take a couple minutes to finish completing the rows in this column for your predicted values using your t values here, respectively. Now, these are the values you should have gotten for your predicted y values here. Did you get them? If not, pause the video again and go back and make sure that you use this equation with the respective t's here. So for example, you would have 0.5 for this one, you would have 0.5 times 2 plus 8, and you should get 9. Okay? Now, our second step here is we want to add 2 new columns for the residual and their squares. So what we're going to do, if you look above in the table, I added 2 blue columns. They're already here. They're in blue to indicate that they are not needed until the second step. Okay, so you have your residual is y minus your predicted, or your observed minus your predicted values. So here you would have your 9 minus 8, which is equal to 1. And then the last column here, row 1, you would have, that would be 1 squared equals 1 to find its residual. Pause the video, take a minute or two, and complete the rows in the last 2 columns. Okay? Feel free to use your calculators if you wish. I don't think it's necessary here, but you are free to use it. All right, now, so these are the remaining values that you should have gotten. If not, take a minute, pause your video, find out where the error was. Again, remember you're taking your observed y value, for here's 9, and then you're subtracting your predicted value to get your residual, which is 0. And then in the last column, you're taking your residual and you're squaring it to find out what you get. Okay? So remember, we want to find our sum of squares error, okay? So the sum of squares error is the sum of your residual squared. So that's the point of getting to this final column here. And what we're going to do to find our sum of squares error, we are going to take these values and add them up to see what we get. That's our sum of squares error. So this would give us 1 plus 0 plus 0 plus 0. You really don't have to write the zeros in, but you can. Plus 1 plus 1 plus 1 plus 4. And whenever we add all of that up, we get 8. So our sum of squares error is 8 for our first model, y hat equals 0.5t plus 8. Okay, so now what we want to do is repeat this process using the second model. So now repeat this process using the second model. Y equals 0.25t plus 9. I've already put your t values here and your observed values, your observed y values here. Take a few minutes, pause the video, take a few minutes to find out your predicted value, your residual, which is given by y minus y hat. Again, take this y minus this y hat and you'll get this value. And then in this last column, take this value and square it here. Okay, so pause the video, take a few minutes and complete the table above. And I left some space here for you to do your scratch work. Okay, I'll be waiting for you. All right, once you've taken the time to compute your values, your predicted, your residual, and your residual squared, that is a squared here, then what you should get are these values here. And remember, our goal is to find our sum of squares error. So what we're going to do is we're going to add 0 plus 0.25 plus 0 plus 0.25 plus 0 plus 0.25 plus 1 plus 0.25. And adding all of that up, you have 4 quarters, not erasing it. You have 4 quarters here, so that gives you 1 plus 1 is 2. So you have your sum of squares error here is 2, which is certainly smaller than 8. So what that tells us is the second model is a better fit for our data. It's a better fit for our data. So if you take a minute and you plot the data points and the two linear models, you have those sketched, then you will see that graphically. And what I recommend now is taking a minute to graph both. You can take your graphing calculators, plot the data points, and you can sketch the respective lines. You can also use Desmos to graph these, so let me explain to you how to do that. So if you go to desmos.com and click graphing calculator, then if you click the plus here and you click the table, then we can add our points here from our table, but instead of, and from my table 1 on page 2, but instead of reading vertically like we've been doing, we're going to now read them horizontally. So whenever, instead of X, you will have T1. So your first T was 0. So you type in 0, press the tab key, then you'll be able to put in the corresponding Y. Press tab, it'll take you back down where you can enter your next T value, which was 2. Your Y value was 9. Tab again, you can enter 4 and 10. Remember, tab to get to the next position. So you would then have 6, and you tab again, you have 11, and you have 8, and then you have 11 as your corresponding Y. And if you zoom in a little bit, then you'll be able to see as you type your values in, it's actually plotting them. It's actually plotting them so you can see them. So let's continue. We plot 10, 12. Our next one was 12, 13, and then 14, 13. So now you have your data points all here, okay? And now we want to plot our linear models to see if we can see visually that the second model is our better fit. So let's plot the graph here. So let's go to enter f of x. So I just added, and then we're going to click the expression. You can type in y equals 0.5 t plus 8, and that's one graph. And then we want to graph y equals 0.25 t plus 9. And look at there. We do have that this is indeed our better fit. It's our better fit compared to our first model here. Okay? So again, you can use Desmos to help you out here. And you can also use that in your homework too, but make sure you follow the instructions for each problem. Now, among all possible lines, there's only one line with the least possible value of your sum of squares error. So in particular, the greatest possible accuracy as a model. So this actually has a name, and that's the whole point of this section, is to get to this point. So I'm going to zoom in a little bit, make this a little larger, and let's complete the following definition. The regression line also called your least squares line, or your best fit line. And I've been asking you about the best fit. Okay? So the regression line associated with the points x1, y1, x2, y2, out to xn, yn is the line that gives the minimum sum of squares error. The regression line is y equals mx plus b, where m and b are computed as follows. M is equal to n times the sum of xy minus the sum of x times the sum of y, divided by n times the sum of x squared minus the sum of x quantity squared. B is equal to the sum of y minus m times the sum of x, or the quantity the sum of x, all of that divided by n, and note that n is the number of data points you have. The quantities m and b are called the regression coefficients. Now this notation may seem a little intimidating, but really all it is shorthand for is adding a certain number of things or adding specific things. So let's talk about the notation a little bit. So this notation sigma means sum, and it's a fancy way of adding. Sigma x means the sum of the x values. So we say that this is the sum of the x values. So in other words, this is x1 plus x2 plus everything out to xn. And the xi are coming from your points, your data points. The sum of xy is the sum of your products. So you're taking your x values and your y values and you're multiplying them in the respective coordinates. So you have x1, y1, x1 times y1, plus x2 times y2, plus everything out to xn, yn. And we say everything out to means you do all of your possible products and add them. Okay? Now the sum of x squared means your sum of squares of the x values. So that means you take the square of x1 plus x2 squared plus x3 squared plus everything out to xn squared. And whenever we have the sum of x quantity squared, that means you have the square of sigma x, or the sum of x, which means the process is you sum the x values and then you square that sum. So in other words, this would be equal to x1 plus x2 plus everything out to xn, and then you're going to square that. Okay, so let's look at an example here. Of linear regression. We want to find the best fit linear model for the data from Table 1, page 2, and use the model to predict the per capita gross domestic product in Mexico in 2016. So I've already filled in our x values, so now we need to put in our y values here. So take a minute and go ahead and enter your y values, and just pause the video and go back and do that. So these are the values you should have for your y values. Now we're going to find the product, x times y. So we're going to multiply 0 times 9, we get 0. Then we're going to multiply 2 times 9, we get 18. 4 times 10, we get 40. 6 times 11, we get 66. 8 times 11, we get 88. And you can continue. The remaining values will be 120, 156, and 182. Okay, and in our last column here, what we're going to do is we're going to take our x values and square them. So we're going to take everything from column 1, square it, and put it in the respective row. So 0 squared will be 0, 2 squared is 4, and you can pause the video and finish the column entries there. You would have, hopefully you paused your video. You would get 16, 36, 64, 100, 144, and then 196. And so notice that I saved this last row for the sum. So we're going to sum our x values. So take a minute, sum your x values, write what you get here. Sum your y values, write what you get here. Sum your products, write that result here, and sum your squares and write what you get here. Okay, pause the video and do that. Okay, so you should have gotten your sum of your x's is 56, your sum of your y's is 88, the sum of your xy, your products, is 670, and the sum of your x squareds are 560. So remember, n is the number of data points that we have. You have 1, 2, 3, 4, 5, 6, 7, 8 data points. So n is equal to 8. So this means we have 8 times the sum of our product. We got 670 minus the sum of our x, which we had to be 56, times the sum of our y, which is 88. So we have times 56 times 88. We're going to divide that quantity by 8. That's our n. The sum of x squared we found to be 560. Minus the sum of x, which we found to be 56, that quantity squared. And whenever you simplify that, if you're using your calculators, you want to make sure that you put your entire numerator in parentheses, then divide it by your entire denominator in parentheses. Okay, so you can pause the video and do that calculation, and when you do, you get that it's 0.321. I recommend that you enter that into your calculators. Now the wavy equals means approximately. Okay, so that's our m. Our m is 0.321, so that's our slope. Okay, now b, or that's one of our regression coefficients. B is equal to the sum of y minus m times the sum of x, all of that over an n. So that's equal to the sum of y, we found to be 88, minus m, which we have is 0.321, times the sum of x, which is 56. Divide all of that by n, which is 8. Enter that into your calculators, and you'll get that that's 8.75. So we found out that our regression line, remember it's a line, so it's y equals your regression coefficient m, 0.321, times x, plus 8.75, which is your b. So that's your regression line. Okay, now we want to use our model. This is our model that we came up with. Now we want to use our model to predict the per capita gross domestic product in Mexico in 2016. So what we want to do is we want to substitute x equals 16 in our regression line to get the following. We would have y is equal to 0.321 times 16 plus 8.75, and you'll get that that's approximately 14, or in other words, $14,000 per capita. Okay, now I put here that I want to discuss the correlation coefficient. You'll find this on pages 109 to 110 of your books. So make sure you read through this. I'm going to explain it briefly. Now recall that your sum of squares error measures the sum of the squares of the deviations from the regression line. So in other words, your sum of squares error is a measurement of goodness of fit. Okay, so if your SSE is equal to 0, then all of your points, your data points, are going to be on a straight line. But your sum of squares error depends on the units we use to measure y, and it also depends on the number of data points. So the more data points we use, the larger your SSE tends to be. Now, your SSE, sum of squares error, is used to compare the goodness of fit of two lines to the same data, right? But the thing is about your SSC is we cannot use that SSE to compare the goodness of fit of one line to one set of data with that of another to a different set of data. Statisticians came up with this cool way to remove this dependency. They found a quantity that can be used to compare the goodness of fit of lines to different data sets. And that is called the coefficient of correlation, or what I tend to call it, your correlation coefficient. And again, the correlation coefficient is a quantity that can be used to compare the goodness of fit of lines to different data sets, and it's very useful. So make sure you read through this on pages 109 to 110. Okay? And one thing to note, we typically denote the coefficient of correlation, or your correlation coefficient, as R. And there are several different interpretations you can have. R is normally between -1 and 1. The closer R is to -1 or 1, the better the fit will be. And if R is equal to 1 or -1, then all your data points lie on the exact same regression line. Okay? So make sure you read through the correlation coefficient and look through the example.